Okay, we'll get started. So thank you very much for braving the cold, wintry afternoon and come to listen to the latest presentation in the Faculty of Engineering. Now, the next half hour or so, I'm going to talk about my home school, my discipline of Electrical Electronic Engineering. And my name's up there. Okay. So for those of you who've been to the earlier talk this morning for the general engineering, I apologise for the next little repetition of that, what engineering is. I thought I'd get off into a common ground and say it is that engineering are basic activities of professionals who apply scientific principles and professional skills to analyse, design and develop technological solutions to the benefits of humankind. All right, so that's a fairly lofty but fairly broad scope. My home discipline, Electrical Electronic Engineering, the principal domains are electromagnetic phenomena. Now, it sounds a little dry, and I promise you it won't stay this way for too long. But to illustrate what we consider our discipline is about, allow me to go back a little bit indulge in a bit of history and just rewind back 10 years. Right? Doesn't seem that long, but 10 years is an awful lot for the aspiring university students in the audience, but for your parents, I assure you, it's not that long ago. Right? So what happened in 2002, what I'm going to show you is the pace of technological change. So for instance, I dug this up. 10 years ago, the best-selling mobile phone is the little clunker on the left-hand side. I had one of these. It was very useful in its day, but it is a long way away from the best-selling phone of 9 years later, last year, which was one of the smartphones shown up there. Okay. A more typical benchmark is talk about computations, right? One of the core inventions of electrical electronic engineering, computers. 10 years ago, we had the Earth simulator as being the fastest supercomputer according to the top 500 list. And in that machine, there are 5,000 cores running at 41 what's called teraflops, right? 10 to the 12th operations per second. Last year, or currently, sorry, the top of the heap is the Blue Gene Q from the IBM corporation. Look at the number of cores. 157,000 cores and running at 20,000 teraflops. So it's gone up by 50 folds. All right. And the last one, you might all think, well, what's social networking got to do with electronic engineering? Well, 10 years ago, Facebook and Twitter had none, zero, all right, users. They weren't in existence yet. If they were, they were in an experimental form in a dorm room. Okay. Now, Facebook, and this is much publicised when they had the IPO a few weeks ago. They had nearly 1 billion users. And Twitter had about half that. Okay? Now, and have a look at, as a proxy for overall technological demand, I decided to take a look at one simple metric. That is the world electricity generation total. All right? So you can see the general trend of the graph over 40 years, from 1971 to about a couple of years ago. This is the data from International Energy Agency. You see the relentless rise in the generation of electricity, and therefore it is being a proxy for the use of technology in our daily lives. Okay? It shows a clear trend that is not likely to change, even though the Great Recession has done a little bit to taper that somewhat. Another note I might point you towards, because the fonts are really small as a result of the data, the top slice here is due to geothermal and other solar and wind and the kind of renewable resources that are new to the game. The slice of the pie is actually growing a lot larger, all right, despite the fact that it's still fairly small as an overall percentage. I'll come back to that later in my talk today. So coming from these, I'd like to point you to some opportunities and challenges that our field has identified. First of all, clean technology, clean energy technology. The clean technology industries are poised for growth. This is not my statement, it's actually something from Austrade. In Australia, all right, we are blessed with abundant and diverse renewable energy resources. Solar, we're very good at. We have plenty of capacity for solar growth, as well as wind energy generations. Some things on the horizon that might even cause this to be even more attractive to be exploited is the impact of regulations. Right? The much talked about carbon tax is going to levy a somewhat competitive disadvantage, perhaps, for the traditional generation modes. So it calls for investment into the renewable energy sector. Of that, the government Agency for Renewable Energy Resources has pledged $3.2 billion of funding in the next 5 to 10 years. And likewise, the government has set aside $5.5 billion of energy security fund that could further help this growth. Elsewhere, if you look a little bit broader beyond our country, we say the economic strains, this is an article, very recent, a few weeks ago, on economic strains have shown that despite the global economic troubles, it's showing that there's relatively little impact on the tech job opportunities in the wider region. So it spells to you that, well, despite the volatility in global economic conditions, being within the tech sector has certain advantages, right, when it comes to your employment and career. On the flip side, there's more and more talk of the global talent pool, right? Because there's a more increasingly globalized economy, the reaches of companies go further. As a result, where they can recruit is also more diverse. So we have the amazing statistic of having over 1 million engineering graduates in China and India alone. This is per annum. Every year, 1 million engineers are being graduated in these countries. Fortunately for us, in an advanced economy, is that there's a premium on stronger skill base, what's loosely called a global employability. Out of the 1 million in China and India, vast majority of them are not globally employable in the sense that they lack some of the more sophisticated engineering, core technical, communications and business skills that the advanced countries tend to produce. But you can almost guarantee that that gap would narrow as we go along. So, in response to this, at this university, our school, Electrical Electronic Engineering, design our undergraduate offerings based on the 4 basic premises I've up there. First thing is, the programs have a firm focus on fundamental principles. These are the core scientific principles that won't change. Right? That won't change with technology. The way they'll be used will change, of course, but the core scientific principles will not change. We have a diverse range of subdisciplines, so you can, I'll talk more a little bit about these different disciplines later. Our main focus in putting graduates through a 4-year program is to develop what we call the key graduate attributes. Now these are quite generic. These, on top of the core technical competencies, a lot of these graduate attributes tend to focus on their professional conduct and ability to operate in a wide range of conditions. So in other words, we're trying to prepare these graduates for the more and unforeseeable challenges in the future. Just think back, the little slide earlier, what 10 years ago was like, and who knows what 10 years from now would be like. So we can't really train students to be able, or graduates to be able to work on particular jobs because it would be irresponsible. Instead, we develop attributes that allow them to flourish under a range of different challenges. And the last thing, we pride ourselves of having an undergraduate curriculum. We maintain strong links with cutting-edge research. Being a research-intensive university, right, all of our activities are underpinned by strong research. A little graphic, career paths. Adelaide E&E graduates have known to work in the whole list of industries on the left. Is not even exhaustive, just some sample examples, just samples. On the right-hand side, you have some stars, not because we don't like Queensland, we haven't updated it all this year. We definitely have graduates working all over the country, but more importantly, if you actually look around all over the world, our graduates make an impact in terms of developing the career paths globally. So let me spend a few minutes and talk to you about some of the activities related to the research and the kind of expertise that we have within our department. Firstly, I'll group them fairly generically, but under the headings of where this work can be applied. For instance, energy infrastructure It's already been identified as one of the main growth areas in Australia. And some of the work that we do in our school with some of our research professors, some of our research fellows, as well as the teaching academics, we do things within power systems analysis. We have a traditional strength in this area. We have an ongoing investment in electrical machines research, renewable energy resource generation, and the kind of opportunities it brings when it's connected to the main power grid. Fault detection and conditioning monitoring is an exciting area where when we have a really large and geographically dispersed network such as the national power grid, when faults happen, it's awfully hard to find out where they are. Now, it's important to develop technologies and techniques to actually condition and monitor where the faults can be and look at and monitor the entire performance of the entire network. Another area where we have a lot of expertise in is in the health, medicine and bio-inspired systems areas. So traditionally involves things like biomedical engineering, devices that you can wear. Then more recently we have signal analysis. Now these are examples of biological signals like ECGs and EEGs. We have active researchers in working on the processing of MRI images as well as mammograms to help early diagnostic of patients. We also have Australia's largest terahertz facility. It's a national terahertz facility where extensive research is done on terahertz sciences. That's related to the understanding of protein structures as well as exploring exciting future applications such as personalised medicines and the likes. And we also have bio-inspired systems interests. One of the traditionally strong areas in our school has been investments in bio-inspired vision chips. And now more recently there's work on bio-inspired digital architectures, so to trying to understand artificial intelligent systems and try to replicate them in artificial systems. We have strength in telecommunications in a number of areas. In particular, we have a vibrant research group working on antenna design and novel structures and novel materials for embedding antennas. For instance, one of the more exciting projects I like to talk to you about is the idea of using printable materials on just ordinary fabrics to use as antennas. So you can wear your antennas and use them for your gadgets. We also have a strong interest in telecommunication protocols and data networks. And the final area I'd like to highlight today is the area of sensing and environmental monitoring. Now, this is actually very, very broad. It's more than just looking at the CO2 levels at different places. It's also about having the devices to enable that sort of scientific programs. We have low power electronics as a focused research area. We have high performance computing necessary to process the enormous amounts of data coming from these networks. We have core signal processing expertise. We have activities with weather radars, working on trying to detect and better monitor the weather patterns around South Australia. A lot of work on sensor networks and steered array processing, where we can get a lot of aggregate the information from a large number of sensors, and a lot of work on GPS and integrated systems. So, work in these careers, are these rewarding? Well, this is perhaps the more direct advertisement, if you like, are the kind of engineering careers and the kind of remuneration packages that are coming on offer. Mind you, however, that this is just a snapshot of the current market. For instance, I dragged these numbers out earlier this week. They fluctuate based mainly on what's advertised, and over the space of 5-10 years, the different disciplines do swap places every now and then. However, it must be said that the overall volatility of the engineering profession is not great. It's not great because it's fairly stable. And in the US, the median salaries and Australian average salaries are presented up there. Mind you, though, these are the average salaries of all postings on the careers website, and not your typical graduate package. It's not quite as attractive as those numbers suggest. Right. But this is perhaps a longer horizon, and over longer time horizons, this is the kind of packages that are on offer for professional engineers. Now, within our school, all right, we offer a number of different programs. So I'd like to spend some time telling you some of the features in these different engineering programs. The first one I talk about is the Electrical Electronic Engineering program. This is our traditional degree program. It offers the greatest breadth. Right? It offers you a foundation in almost all the disciplines that I mentioned just previously, in all the different areas, such as telecommunications, bioengineering, and sensing and whatnot. The basic scientific principles underlying all those exciting areas are covered in this particular degree program. So most major subdisciplines that underpin those activities, such as microelectronics, signal and information processing, electromagnetics, RF systems, power and machines, and telecommunications and control, these all covered within the 4-year electrical electronic engineering program. At this point, I'd like to do a little bit of advertisement, if you like. One of our alumni is Professor Chok. He's currently based in Japan, right? And he's known as an inventor and a mixed reality expert, where mixed reality is a fairly exciting, and I'd say personally I find it a rather cool technology, because it allows you to have from the low end things like your mobile phone apps, where you can superimpose different sources of information onto your camera. So instead of looking down the street, you can have different bits of information superimposed onto the reality that you observe as it sees fit. So it's geolocation dependent, so it's sensitive to where you are and what kind of interest you have and whatnot. But there are also serious applications for this, such as assisting surgeons to do surgery. When they're operating on a patient, it's useful to have auxiliary information superimposed on what they can see. And he's graduated from our university a little over 15 years ago. So it's done. Now, within the electrical electronic engineering, one of our recent initiatives is to have a specialization in what is an area known as avionics. Avionics is one of those areas that's a little bit hard to explain, but I'll try to do it anyway. If you think of aviation as the systems that can fly, the avionics are perhaps the electronic brains behind the operation. So the kind of technology that goes into an avionics system includes what we call MEM systems, microelectromechanical systems. They are useful. They're commonly found used in these, as well as having heads-up displays and whatnot that are used very useful fighter pilots. As well as system integration is an important part of avionics engineering, because you have all these disparate and functionally important systems that you need to put all together and make sure everything functions as one. One of the most well-publicized and recent examples would be the Curiosity rover, Mars rover, that NASA sent onto Mars last week, or a couple of weeks ago, sorry. And some of the aspects, majority of the systems you might think as mechanical engineering systems, but a lot of the actual smarts behind and the integration behind the Curiosity rover are the works of avionics and electronic engineers. For instance, it is well publicized that when it first landed, it had to undergo a very careful and very well orchestrated landing maneuver, because it's a really large vehicle landing in a foreign planet. And after it was done, the actual brains or the computer software has to be updated, just like you update your laptops, for instance, so that it changes mode from landing mode to the more operational mode, which is doing. All that stuff involves deep knowledge and expertise in embedded systems and software engineering and whatnot. We have a degree in electrical sustainable energy, where we take the base of our electrical electronic engineering degree, the kind of scientific fundamentals, and apply a little bit more towards renewable energy sources. There's much more studies on how the renewable energy generation technologies work and how they impact and influence power systems. And there's a much greater focus on sustainability engineering. Computer systems engineering has been around for little over 2 decades. Now, the focus on this particular degree is also take our basic electrical electronic engineering degree, but spend more time studying systems like embedded computers. Consumer electronics is an area that we look at, and this is an area where the technology that we teach in our program can find an application in the future. What we show here is an example of students looking at a layout of an early microchip. Okay, this is quite old now. On the other hand, we have a real student project. Looks awfully complicated, but is an example of the kind of work that must be completed in a lot of these electronic systems. This here is a takeout from an iPad, okay, not the most current one. It's something our colleagues taken apart at Open Day last year. And the iPad, I was going to show you, if you look at the little processor, that says A4 here, it's a family of processors that is developed by a company in America which focuses on low power, high performance embedded processors. And a couple of our graduates, one rather recent, Dr. Kelly's very recent graduate of our school, they are working on this type of project. And on the right-hand side, we have a little older alumni. I hope he doesn't mind me calling him a little bit older, but he's spent over 10 years working across America, working at really influential firms as a computer architect, which means he makes the decisions on designing the core computer systems and how the brain of your processors work, whether they are high-performance computers or in your tablets and mobile devices of the future. And we have a degree in Telecommunications Engineering, Bachelor of Telecoms, where, again, the base of the degree is based on electrical electronic engineering, but there's a lot more emphasis on the range of telecommunication applications that are currently in use. For instance, voice telephony, you may think it's a very old-fashioned, but underpinning the technology behind voice telephony is a lot of the principles that also apply to the other systems such as data transmission networks, multimedia networks, and the kind of work that goes into image and multimedia communication. You need a lot of the basic fundamental knowledge that we teach in electrical electronic engineering. For instance, you need intimate knowledge of how electronic systems work, how propagation systems work, as well as how the signal processing algorithms to make everything fit within the kind of bandwidth allowances. Now, looking forward in the future, in Australia we have 2 major projects, one very well publicised. It's politically a bit of a hot potato, the NBN Co, right? They're rolling out the National Broadband Fibre Network. And the other would be the Square Kilometre Array, in which Australia is playing a major role. These 2 areas will need expertise in telecommunications engineering for many years to come. Now, the final little advertisement of our alumni is Professor Neil Westy. He's a Wi-Fi pioneer. He worked, in fact, his company, and there's a little patent his company is owned, was the first to invent the mobile wireless chipset for use for your laptop. So he was the first one there, and being the first one means he's richly rewarded, and I mean richly in the financial sense, when his company got taken over by Cisco Systems a bit over 10 years ago. So in summary, these are the kind of offerings we have. These are a summary of all the offerings. We have Bachelor of Engineering, Computer Systems, Electrical Electronic, and Electrical Electronic with the specialisation in Avionics, Electrical and Sustainable Energy, and Telecommunications Engineering. And there's some further finer details such as double or combined degree offerings. If you want more information, you're more than welcome to talk to us later today. So in the last few minutes of the talk, I'd like to tell you a little bit about degree structure, in particular more focused on the first year experience and what it'll be like if you do join us and spend your first year with us. So level 1, it's the major components are mathematics, physics, computer science, and electronic engineering, of course, right? So these are the 4 main areas. But we look at trying to develop part of the what I talked about in developing graduate attributes, we'll start developing those right from the first year. And they broadly into 3 categories. They're the theoretical kinds, the practical graduate attributes, and most importantly, the professional graduate attributes. So a little bit more about those. The theoretical attributes, we'll look at, in the first year, you study the principles of electronical circuits and electronic systems. You look at digital they function. We'll look at electrical energy, in particular, principles on alternating current applications, entry-level electronic engineering, and some of the real practical and lecture work in the first year. Now, in the practical, you have to take the principles that we teach you in the theoretical lectures and apply them in weekly sessions. So in 2 semesters, we have 2 broad themes. In the first semester, the theme is digital electronics. That's the thing on the left-hand side. I showed you this picture a little bit earlier. It's straight from first year work, right, where you'll be building this thing right from the get-go in semester 1. In semester 2, when we develop a bit more of the theoretical knowledge, such as alternating currents, then we look at analog electronic systems, where this is an example of a student radio. And if you tune it properly, you can listen to the commercial AM broadcast. So it's handy in summer for the cricket, and just in time for that. Now, in level 1, you also do some professional work where students are immersed in an environment that allows them to develop their professional attributes. For instance, they'll be working in teams, so they can work on collaboration. They'll also be working on their leadership skills and how they manage themselves professionally, time management, resource management, and the likes. They will need to communicate with each other. One of the most underrated ability for engineers is the ability to communicate. People very often think of engineers as, a little bit archetypal. Americans call it the eggheads. We're a little bit geeky and we're good at maths and that sort of skills. It's far from the truth. The most successful engineers are brilliant communicators, because it is important to cut across the key technological challenges and explain to different stakeholders, whether they are your investors, your customers, or the government regulators, or the wider public. They will have to work on reporting, less glamorous side of things, but an essential part of life as a professional. You have to write reports. We'll also expose them to what's called ethical behaviour and what's not. Right? In high school, typically you don't get a chance to discuss or practice these knowledge. In the first year setting, we will. And then there'll be tours of local companies. One of the most popular activities in first years is the outing to the Telstra exchange in the middle of town. And okay, now subsequent years, if you survive first year, okay, which sounds hard, but let me reassure you, the vast majority do. Okay, subsequent years would be focused on a range of different activities. Now, the second year, you're doing more of the fundamentals. So there's still a component of mathematics and engineering, computer science, and within engineering, you'll cover the 4 major subdisciplines or the beginning of those. Okay, and level 3 will develop some more specialized courses when you become more specialized in the different subdisciplines, as well as core engineering and management skills to be further developed on that. By final year, when you're actually just about to graduate, we'll definitely put you through a project, okay? It's important to be able to do stuff, right, rather than just completing your homework and the likes. And then there will be more sections on management. You do courses to prepare you again for your work outside as a professional. And there'll be further chances to specialise and take on particular electives that takes you fancy. So this is what students say. Sample some student feedback. We have many avenues to extract student feedback. Okay, and this is just a small collection of what the students are saying. Okay. Now, because of the time constraints and the fact that I can't really read them all out to you, I'm more than happy to discuss these with you later on outside beyond this talk. So I'll finish off on this slide saying this is more information about the the degree programs in general, applying for Adelaide degree programs. The School of Electrical Electronic Engineering will be in the display area between Incarni Wadley building and the Engineering North building. If you don't know where that is, please look for signs. We have a range of student work and staff more than happy to talk to you, and there'll be some students who are eager to show you their actual projects they've completed. Okay, so thank you.